Welcome to the YouTube series AI Paper Slop. Today we're looking at Dion3 full-stack orthogonal updates by Noah Amsel and a joint team from NYU, Princeton, NVIDIA, Yale, and Microsoft Research. And the core insight here is that, well, the Muon optimizer is incredibly effective for training frontier LLMs because it converges in significantly fewer steps than AtomW. But it comes with this brutal cubic time computational overhead because of a math process called the Newton-Schulz orthogonalization step. So Dion3 solves this overhead at literally every level of the stack.
Right. They really attack it from all angles.
Yeah, exactly. It introduces an algorithm called Gram Newton-Schulz to reduce the FLOPs, custom CuteDSL symmetric kernels for Hopper and Blackwell GPUs to double the speed, a fractional update rule that only computes a subset of the momentum matrix, and a megabatching strategy for distributed training. Together, these changes cut Muon's optimizer step time by up to 6x. It takes a staggering 26x compute overhead and crushes it down to just 4x compared to AtomW, all while matching or even slightly improving the model's final loss.
And honestly, if you're an ML engineer or an AI researcher listening right now, and you're tired of AtomW, but you just can't afford Muon's compute tax, this paper is for you. It provides the exact blueprint for making orthogonal optimizers practical at scale.
It really is a lifesaver.
It is, yeah.
Yeah.
It removes the massive engineering hurdles that were previously required to use Muon. We're looking at a full-stack rescue operation of one of the most promising optimizers we have right now.
I love that framing, a rescue operation.
Yeah.
Because before we can dismantle the stack to see how Dion3 fixes Muon, we need to understand exactly why Muon was breaking our compute budgets in the first place.
Oh, it was just entirely suffocating the hardware.
Right, so standard Muon is essentially steepest direction descent with respect to the spectral norm. It uses a polar operation, a polar decomposition, to balance the spectrum of the update. So think of it like SGD with momentum, but with a ridiculously expensive fancy matrix operation slapped right in the middle.
Yeah, and that polar decomposition is just too expensive to compute. Exactly right. You can't just run an exact SVD on massive matrices every single step. So Muon approximates it using the Newton-Schulz iterative method.
Which is still super heavy.
Extremely heavy. It specifically uses a sequence of degree 5 odd polynomials. So to do that approximation, it requires 15 dense matrix multiplications per step. And that costs big O of n cubed time.
Wait, 15 dense matrix multiplications for one step?
Yes, per optimizer step.
Okay, but transformer weights, like mixture of experts layers or grouped query attention, those are highly rectangular matrices, right? If the aspect ratio, which the paper calls alpha, the larger dimension divided by the smaller one, if that's really large, this cubic time math becomes a total nightmare for scalability.
Exactly. It's a massive nightmare. This super linear complexity means that as your models scale up, the optimizer step just starts eating an unacceptable percentage of your total training time.
Just to figure out how to update the weights.
Right. The paper points out that up to 17% of total training time in some Llama 3 supervised fine-tuning scenarios is just the optimizer step. And plus, when you're gathering weight shards across GPUs in distributed training, it creates this massive communication bottleneck on top of the math.
So the math is too heavy, the network is choked. How do we do less math?
You look at the shapes.
Right, by looking at the shapes of the matrices and exploiting symmetry. So this brings us to Dion3's first big trick, which is Gram Newton-Schulz, or GNS. Instead of running 15 iterations on a massive, highly rectangular n by m matrix, GNS computes the n by n symmetric Gram matrix, which is the matrix multiplied by its transpose, and it iterates on that instead.
Yeah, which is mathematically identical.
Mathematically identical, but it saves, what, 55% to 68% of FLOPs?
It's a huge reduction. And it's brilliant for modern LLMs because, well, let's look at Gemma's MLP layers, for example. Those have an aspect ratio of 8x. So by forming the Gram matrix first, this trick drastically shrinks the computational footprint. You trap all those heavy iterations inside a much smaller square matrix.
Okay, I have to play the skeptic here, though. If this is mathematically equivalent and it's way cheaper, why wasn't standard Muon just doing this from day one?
Yeah.
There has to be a catch, right?
Oh, there is a massive catch. It's the finite precision nightmare.
Of course. Floating point math strikes again.
Exactly. When you're training in bfloat 16, forming that Gram matrix introduces tiny, spurious, negative eigenvalues. We're talking microscopic artifacts like -4 times 10 to the -4th.
Which in a theoretical math equation wouldn't exist.
Right. A true Gram matrix is positive, semi-definite. But in B-float 16, you get these tiny negative numbers. And because the Newton-Schulz loop approximates inverse square roots,
Well, you can't take the square root of a negative number.
you cannot. So these tiny negative artifacts get fed into the loop and they blow up exponentially. Within a few iterations, they fill the whole matrix with infinities, and the model completely diverges. It just crashes.
Wow. Okay, so how do you fix that without losing the speed up?
They came up with a really practical fix.
Restarting. You run the algorithm for just 2 iterations, compute the intermediate matrix, and literally restart the process by reforming the Gram matrix from scratch. This resets the spurious eigenvalues and stabilizes training before the artifacts can blow up.
It's basically a mathematical garbage collection mid-flight. It's so smart. And then there's the hardware layer of this fix.
Right, because the Gram matrix is perfectly symmetric.
Exactly. Since it's symmetric, the authors wrote custom CuteDSL GMM kernels specifically for Hopper and Blackwell GPUs. Standard couplets would just blindly compute the whole matrix, wasting cycles.
Right, calculating the top half and the bottom half even though they're identical.
Exactly. So instead of doing that, the custom kernel only computes the lower triangle. It does half the math, and then it just copies it to the upper triangle in the epilogue phase. This alone yields a massive 2x speedup over standard couplets.
That is just deeply satisfying engineering. But okay, we've optimized the math, we've optimized the GPU kernels, but the most efficient computation is the one you just don't do at all, right?
Oh, absolutely.
So what if we just shrink the matrix before we even touch it? This leads to the fractional update rule.
This is the really radical part of the paper.
It blew my mind. At each optimizer step, Dion3 selects only a fraction of the rows, say 25%, so an F of 1/4 of the momentum matrix. But it picks the ones with the largest L1 norm. It orthogonalizes only that chunk and updates only those weights.
Right, and people naturally wonder, wait, what happens to the 75% of the rows you just ignored?
Yeah, you can't just throw away 3/4 of your gradient data.
You're not throwing it away. This is where error feedback comes in, and it's genius. Normally, you decay the whole momentum matrix by the standard factor, mu, but here, you only decay the selected rows.
Ah, so the ignored rows aren't decayed.
Exactly. The 75% you ignored just sit there. They keep accumulating new gradient signals step after step until they finally trigger that L1 norm threshold, and then they get selected in a future step.
So it's like a loyalty rewards program. You're constantly earning points from the gradients, but you don't actually spend a compute to update the model until you hit a minimum balance.
That is a perfect way to think about it. The information is delayed, not lost.
But here's the wildest finding from the paper. Doing less work actually resulted in a better validation loss. Training 1B to 14B parameter models, Dion3 with an F of 1/8 or 1/4 beat the fully tuned NorMuon baseline in cross-entropy loss and on downstream benchmark.
I know, it's completely counterintuitive. You do less work and get a smarter model. But I should address the listener directly here with a crucial tuning rule, because if you try this in your own runs, remember that updating fewer rows means a smaller effective step size across the model.
Right, you're moving less of the model at a time.
Exactly. So the authors provide a strict transfer rule. Your learning rate must scale proportionally to the square root of 1 over f.
Let me do the math on that really quick. So if I use a 1/4 fraction, 1 over f is 4, the square root of 4 is 2, so I have to double my learning rate.
Yes, exactly. If you drop to a 1/8 fraction, you scale the learning rate up by the square root of 8. If you don't do this, your model will underperform because it's just not taking large enough steps on the sparse dimensions.
That is such a vital detail.
Mhm.
Okay, so the compute is finally fast. We've optimized the FLOPs, we have symmetric kernels, and we're only updating 25% of the rows. But for AI researchers training on thousands of GPUs, compute isn't the only enemy.
No, not at all.
Communication latency is a massive bottleneck.
Yeah, when you're using fully sharded data parallelism, or FSDP, your momentum matrices are split across the GPUs. So to run Newton-Schulz, you have to gather them using all-to-all communications.
And doing this layer by layer creates a massive traffic jam because the messages are too small to saturate in link bandwidth. So you're just paying flat latency penalties over and over again.
Right. The hardware has a latency floor about 25 microseconds just to start a message. If you send tiny shards, you pay that toll thousands of times.
It's like having a huge highway but only sending single cars down it, and every car stops at a toll booth.
Exactly. So Dion3 introduces megabatching to fix this. Since transformers only have a handful of distinct weight shapes, like all the attention projections are one shape, MLPs are another, the Dion package groups all local momentum shards of the same shape together into one giant all-to-all communication.
So they put all the cars on a massive bus.
Yes. And this reduces the communication rounds to a small constant big O of 1. It becomes completely independent of the model's depth.
That's incredible. And the metrics reflect that. For a 1 billion parameter model scattered across 8 FSDP shards, megabatching cuts the optimizer step time by an additional 35%.
Just by hiding the latency. And there's a massive bonus here for multi-pod clusters like data center networks or DCNs.
But because DCNs are notoriously slow. Right.
Extremely slow compared to NVLink. But they get what the paper calls compressed data parallelism. Because of the fractional update rule we talked about earlier, you only need to sync the selected rows across the slow data center network.
Because the unselected rows didn't change.
Exactly. You naturally cut your interpod communication volume by 75% if you're using an F of 1/4. It dramatically reduces the bottleneck without any lossy compression algorithms.
Okay, let's zoom out and look at the final scoreboard here. By stacking the symmetric kernels, Gram Newton-Schulz, the 25% fractional update, and megabatching, Dion3 brings this staggering 26x Atom W overhead down to just 4x.
It's a true full-stack rescue of the Muon optimizer.
It really is. But before we wrap up, you mentioned earlier there's a deeper theoretical question here for everyone listening.
Yeah, there is. Because, the most surprising result here isn't the speed up. It's that updating only 12.5% or 25% of the matrix at a time improved the model's loss. And this mirrors recent, unrelated findings that randomly masking SGD updates actually improves optimization trajectories.
So it's not just a speed hack.
Right. So as you design your next training run, ask yourself, is doing less work just a hardware hack? Or is sparse fractional updating acting as a powerful new form of implicit regularization?
Like maybe our optimizers are currently just doing too much all at once and it's adding noise.
Exactly. Maybe starving the updates a little bit forces the model to learn a better representations.
Man, that is a fascinating thought to leave on. Well, that wraps up this breakdown. If you're looking to implement this, definitely check out the open source Dion and Gram Newton-Schulz packages to try it in your own pipelines. Thanks for tuning in to the YouTube series AI Paper Slop, and we'll see you in the next one.